start off with. So, okay, so let me share my screen here so we can talk about those. Where it is? There it is. Good. And good. So, good. So the first one, so this is the first group assignment we're going to talk about, and then I'll put you off in your breakout rooms. And again, I'll give you about 20 minutes or so to kind of start talking about them amongst yourselves. And like I said, I'll periodically be going around to all the different groups and kind of checking on everybody and seeing how everybody's doing. But the first one says that here we have mass M1 with initial velocity of 8 meters per second sliding to the right, okay? So then it's going to make an elastic collision with M2, where M2 is attached to a spring which has a spring constant of 1,208.5 newtons per meter, which then sends M2 under harmonic oscillation, which has a period of 14 seconds. So it goes from equilibrium to negative of the amplitude to the amplitude back to equilibrium in 0.14 seconds. At which point, M1 then slides back to the left with a new initial, well, the new velocity because it has made an elastic collision. At which point then it's going to rocket off of that little cliff here, which has a height of 4.9 meters, and it's going to undergo projectile motion until it hits the ground, the 4.9 meters below. So basically, what you want to do then is first determine what is the mass of M2, because you're going to need the mass of M2 to figure out how fast M1 is going after it collides. Then you want to determine how fast is M1 going after the collision. And then finally for part C, you want to figure out how far does it actually fly to the left. So what is that distance D that it ends up going after it has fallen down? So basically the point of this is to kind of think about how the harmonic oscillation comes into account, and to, for those who haven't actually seen Physics 1 in a little while, start thinking about all these different things of conservation of momentum and projectile motion and kinematic equations, all those wonderful things that will show up during this class. So first of all, let me go to our previous page. Some helpful equations I will give you here for group assignment number 1 is that these are the general solutions for 1D elastic collision. So what this says then is that the velocity of the first object after the collision, that's v1 prime here, is then equal to the initial velocity of v1 times then the difference between m1 and m2 plus twice the mass of m2 times v2, all divided by the sum of the masses. Now, in our case, v2 is simply equal to 0 because initially it's stationary. So that initial velocity of mass m2 is simply equal to 0, which means this whole entire term is going to go away. v2 prime, so this is the velocity after the collision of the second object of the m2 here. That's then equal to v2 times m2 minus m1 plus 2m1 v1 divided by m1 plus m2. But again, v2 is simply equal to 0, so this term is going to go away. Now, as far as the group assignment is concerned, the only one we care about is this one. The other one is actually, it's nice to know, but we don't need it for this particular problem. So again, let's go back to the question. So again, this one's moving to the right at 8 meters per second, makes an elastic collision, is then going to fly off in the opposite direction. So after the collision, it's going to move to the left. So we want to know how fast it's moving. And then how far does it go under projectile motion? And then again, this thing is oscillating now back and forth with a period of 0.14 seconds. And we want to know what is the mass of m2 because we need that to determine that velocity of v1 prime here. Okay. So how many people do we have? I didn't count. We got 14, I think, including me, so it's 13. So we can do, so let's do 3 breakout rooms. So why don't we do that? All right, so let me stop sharing my screen. So let's go to the 3 breakout rooms. So in this case, I'm gonna split you all up into 3 rooms. You'll be randomly put into different rooms. Again, the idea is to talk together, to work together, to figure out how to actually do these problems, do some peer learning and some peer understanding. And again, I'll be going to all the different rooms, kind of checking on you guys, asking questions, and don't be afraid to ask questions, right? So, and off we go. Taylor, you just have to decide to join the room or not. Looks like my having. There we go. Good.
Okay. So we first have to find the mass of block 2.
Which is the one attached to the spring. So we're given the spring constant, right?
Yeah.
And the period. So we can use the same thing that we used in lab to find the mass.
Which is that, what's that equation? It's
The T equals 2 pi square root of the mass over spring constant.
yes.
You just have to rearrange it.
Sounds
Do
like
we have to use the
a
one?
good start. Good.
Do we have to use the equation with the W in it, or do we have to use just the one that we used in lab?
We're not given the frequency, so I would use the one that we used in lab. We have the given.
That's right. And which mass are you using? So are you using M1 or M2 or a combination of M1 and M2? So which one is actually harmonically oscillating?
M2.
Good. So you're only going to use M2 in this case. That's right. Fun. All right. I'll be back.
I should have brought a calculator.
All right. How are we doing so far, ladies?
Great.
Good.
So have you determined how to actually calculate M2?
We're trying a couple different things right now, I think.
Okay. So what's the ideas? So what,
I started with I took like the period, the 2 pi over t, and then got the radians per second, and then now I'm just plugging it back in to find them.
okay. Effectively, yes. Yeah, you're using the same period that you did in the lab. That's right. So you're saying the period then is related to the mass. So the only question then is, which mass is it? So are you going to use M1, or are you going to use M2, or are you going to use both M1 and M2? So the question is, which one is harmonically oscillating? So are they both oscillating, or just M1 or M2? Molly, you said something, but I couldn't hear what you said.
Oh, sorry. I was just talking to myself.
Oh, gotcha. The best way to get answers. That's right. So what do you think? So which one is actually harmonically oscillating? So is it both M1 and M2 together, or just M1, or just M2?
Wouldn't it be M2?
That's right. So just M2. Exactly. So you're exactly right. So you're going to use the period then to find M2. And then once you have M2, then you can figure out what is the velocity for V1 prime. Exactly. Good. That's right. So you'll just use exactly the same period you did in the lab. So period is equal to 2 pi times the square root of the mass divided by the spring constant. Exactly.
Okay.
Very good. Good job, Taylor. All right. Hello, ladies. How are we doing so far?
I think we're doing pretty good.
Doing okay so far? Good. So have we figured out how to calculate M2?
I just used the first equation that you did, I think. That you gave us.
You mean for the velocity ones?
Yeah, is that the right thing to do?
Well, do you know what V1 prime is? You know what V1 is, but do you know what V1 prime is?
No, not really.
No. That's right, Valerie. Good. So if you were going to use just that one, then you would have how many unknowns in that one equation?
Too many.
Too many. Exactly.
I just use V prime is the same as V1, so I put it at as 0.8.
Well, the only way that would be true is if M2 was infinite in mass, basically.
Okay.
So, for example, if you ran into a wall and you bounce off the wall, then your initial velocity would be the same. It would just be in the opposite direction. So if you ran at the wall at 8 meters per second, you would bounce off with a negative 8 meters per second because the mass of the wall is so much more than you are.
Yeah.
So, but in this case, since we don't know what M2 is, we can't really assume that. But what do we know about M2? What is M2 doing? So after the collision, what does M2 do?
It starts to slide.
It starts to what?
To slide.
Starts to slide, and more importantly, how is it sliding?
In the other direction?
In the other direction? And what else do we know it's doing?
Falling.
Well, that's M1 again. That'll happen afterward. But what is M2 doing? So M2 slides, but it only slides how? Give you a hint. I'm hypnotizing a chicken. So what motion do we call this?
Back and forth?
Back and forth, or harmonic oscillation. There we go. So that's right. So we know M2 is harmonically oscillating, right? So after the collision, M2 is simply harmonic oscillating. So what else do we know about M2? So we know it's harmonically oscillating, and what else are we given in the problem? So we're given the time it takes for it to go through one oscillation, right? So we're given its period. So we know it's harmonically oscillating. We know its period. So from there, we can figure out what is M2. So just like you did in the lab. So in the lab, what you said was that the period was equal to 2 pi times the square root of the mass divided by the spring constant. So here now you know the period. You also know the spring constant. So now you can determine the mass.
Okay, so it'd be 2 pi times the square root of m over
Okay.
128.5.
Yeah, the 1,208.5. That's right. And that's all equal to the period, which is 0.14 seconds.
Oh, okay.
Okay. And which mass is harmonically oscillating? Is it both M1 and M2, or just M1 or just M2?
Just M2.
Just M2. That's right. So that mass that shows up in there is simply M2. So you're just then solving for M2. Good. So from there, you can then get M2 and then move on for the rest. Good. Good job, ladies. I'll be back.
Okay.
How
We're back.
is
We're on
the third part.
And the third part, good.
We got
Oh.
-4 for the second part for the velocity.
Good. Good. Now, when it comes to the third part, you don't have to use that negative. The negative just means it's moving to the left. So as far as the third part's concerned, you can take your coordinate system in the direction of left and then call it positive. So you don't have to use it as negative.
Okay.
So do we remember how to do projectile motion?
No.
No. Good. So remember, for projectile motion, you have to look at the x direction and the y direction separately. So you're going to use the second kinematic equation for both the x direction and the y direction. But what's the acceleration in the x direction, in the horizontal direction? 0. Absolutely. That's right, Adrian. There is no air resistance. So what is the acceleration in the y direction?
Gravity?
Gravity. Exactly, Katie. 9.8 meters per second squared. Now, how we set up our coordinate system will depend if that's positive or negative. So it just doesn't matter. All we care about is that magnitude. So good. Now, what is the initial velocity in the x direction? So you guys already told me it's 4 meters per second. What is the initial velocity in the vertical direction?
0.
0.
Yeah.
So that's right. So in the vertical direction, you're going to have y is equal to the initial height, which in this case is going to be h, right, minus 1/2 gt squared. And then in the y direction, when does it hit the ground? Well, it hits the ground according to our coordinate system when y is equal to 0. So from there, you can then solve for the time it takes for it to hit the ground. Now plug that into the x direction, where the x direction is going to say, well, x is equal to the initial velocity times the time. So in that case, x then is just going to be equal to that 4 meters per second times whatever time you find from the y direction. Everybody's okay with that? So remember, projectile motion, you work with both the x and the y direction. You use one of them to find the time. Use that time into the other one to find what it is that you want. So in this case, we're using the vertical direction to find the time. Use that time into the horizontal direction to find the distance. It's okay?
Okay.
Sounds
So
good?
by your coordinate system, we're starting at a positive height of 4.9 meters, and then
Correct.
ground is 0.
And then you're going down to 0. That's right. That's right. Exactly. If you did it the other way, you can start off at 0, and then you go down a positive 4.9, and then gravity would be positive in that case. That's right. So either way would be fine. All right. Good job, ladies. I will be back.
Gravity, the gravitational force. So you get like the initial velocity. And
What if
then
they're giving time? Isn't that the 2 the time one, not the velocity? I
You
just
talking
remember.
about the third part of the question?
Yeah.
Yeah.
Good, that's right. So, right, projectile motion, you work with both the x and the y direction simultaneously. That's right. So you're right. You would do the y direction to find the time, exactly as Taylor said. So in that case, you know the initial velocity in the y direction is how much? So is it initially falling in the y direction?
No.
No, it's just 0. Good. And what is the acceleration in the y direction?
Gravity.
Gravity, 9.8 meters per second squared. That's right. So good. So, and what about in the x direction? What is the acceleration in the x direction?
Isn't that what we found? The -4?
Well, that's the initial velocity in the x direction. That's right, Taylor. But what is the acceleration in the x direction?
None.
None. Exactly, Taylor. That's right. So there's no air resistance, so there is no acceleration in the x direction. So that's right. So you're going to use your second kinematic equation in both the x and the y directions. Your y direction, you're going to use that to get the time, as Taylor said, and then you're going to use that time back into the x direction to find the distance at which it goes. Exactly. Using that, the acceleration is 0, but the initial velocity is 4 meters per second.
I'm confused what equation that is.
Oh, the second kinematic equation is the one that says x is equal to x initial plus the...
Oh, okay, I'm back now.
Okay.
Good now.
Good.
Forgot about those.
They come back to haunt us. It's okay. All right, is everybody on board?
Yes.
Good. Okay. Sounds good, lady. I'll be back to check on you.
I'm multiplying. Okay. I'm almost there, I swear, guys. God.
And I think I got C, but I'm not sure.
How we doing, ladies?
I think we're doing good.
Good.
We did have a question.
Sure.
How do we turn this in? What do you need from us as far as like turning it in?
Oh, so to turn it in, you won't turn it in until the day of the exam. So basically, if you want, one of you can write everybody else's name on it and then basically take a picture of it or scan it, whichever one is easier. And then on the day of the exam, under the tab of the exam, it's going to have a place to upload your group exercises. So you would just upload the picture or the scanned copy of that. Now, you all can upload your own if you want, or one with everybody's name on it is also sufficient. So, yeah. So some people are better at bookkeeping than others. That one person can keep track of it. Otherwise, you can all upload it as well. But so again, it's being used as 1 point of extra credit towards the exam, as well as saying I was here and I did participation. Kind of double dipping with all of these group assignments.
So on the slide that you gave us for
Yep.
this, it shows you that A, the answer is 0.6. And then for B, it says negative meters per second.
It doesn't say the number?
No, I think maybe you put the number for D, but I'm not positive.
Okay.
I just didn't know because I had got 0.6.
Oh, yeah. Okay. Yeah, sorry. It should be negative 4 meters per second.
Okay, and then
Sorry
is D,
D, I think, is also 4 meters. I believe that's
okay.
because I think it takes 1 second for it to fall, so it should go 4 meters then. Yeah.
Okay.
Yeah.
So for letter C, it says use kinematic equations.
Correct. That's right.
And I used V equals VI over V plus VF over 2 times the period. Would that be right?
Well, in this case, since M1 is moving, it's just simple projectile motion, which means that you would use the way you would solve projectile motion in 175, which means that you would work with both the Y and X direction simultaneously.
Okay.
So you'd look at the Y direction, write down, Y is equal to Y initial plus V initial in the Y direction. And then also in the X direction. But here, since you know all the information in the Y direction, you would then use the Y direction to solve the time, plug that time back into the X direction to find the distance in which it travels.
Okay.
So having said that, what is the initial velocity of M1 in the Y direction?
0.
0, good. What is the acceleration in the Y direction?
0.
Not in the Y direction.
Oh, is that the one that's falling?
Correct. So in the Y direction, it's going to be 9.8 meters per second squared.
Yeah, sorry.
Oh, you're fine. What is the initial velocity in the X direction?
In the X, it would be 0.
Well, the
Right.
acceleration is X in the 0. That's right. But what about the initial velocity in the X direction? So that's just your answer from part B. So that is that velocity that you found. So
negative 4.
that's right. But in this case, you can use it as positive 4. We can always switch the coordinate system in the opposite direction, which will be fine. So that's right. So in the X direction, the initial velocity is 4 meters per second, but there's 0 acceleration because there's no air resistance. In the Y direction, it has 0 initial velocity, and the acceleration is just Again, use your second kinematic equation in the Y direction to find the time. Use that time into the X direction to then find the distance it travels.
Okay.
Everybody's doing okay? Mallory doesn't look convinced, but.
Which kinematic equation should I use?
You're using the second one. So the x is equal to x initial plus v initial in the x direction times time plus 1/2 acceleration times t.
Okay. Sorry. I don't remember a lot of this.
No, you're fine. That's one of the points of doing this question, to try to get you to remember a little bit of the stuff. So.
No, because subtract. So in the actual equation, it's plus 1/2 gt or acceleration t squared. But because we are working in the projectile motion, we're just assuming the negative, and so we
that it's like in free fall. Okay.
Yeah, we just changed the equation before we ever started.
I gotcha. I was like, I suspect you guys are right, but that negative sign is throwing me off. Okay.
Yeah.
So the negative sign comes because your coordinate system points up, but G points down.
Mm-hmm.
So the negative sign comes because G is in the opposite direction of positive. So that's where the negative sign comes from. Because remember, G and V and X are all vectors. So we have to remember that you have to take the direction according to the coordinate system into account. So
I think that's where all the confusion is coming in, because like I'm looking at my notes from 175 and we're talking about it, and it's like I'm looking at notes for an object in free fall and it already had the negative built in. And I was like, wait, what happened?
Gotcha. Yeah, we have to be careful with that negative because it depends on how we take our coordinate system. So
right.
All right. Everybody else doing okay?
We got it.
Good.
Do you want us to move on to the next one, or we just
Well, I'm gonna break everybody up from their rooms in a couple minutes, and then we'll talk about the next one, and then I'll put you back into your rooms.
Okay.
So you might not be with the same group when I go back to the breakout rooms. Actually, no, I'll keep you in the same breakout room. If you want, we can talk about it together now, so that way you stay in the same room, and then I'll just give you more time from there. Do you want to?
That sounds okay.
That sounds okay? Okay. So let me share my screen with you guys. And we'll talk about that problem. And then we'll go back. What's that?
We turn it in around when exam 1 is due?
Correct. Yeah. So basically what'll happen is under the tab for exam 1, you'll see a place where you would submit all extra credit and your group assignments. So you would just take a picture or scan a copy of your group assignments and then upload it under that tab. And if you want, it's up to you guys, but you can all upload your own copy, or you can have one person write everybody's name down and then just upload one of those, and I'll give credit to everybody. So if you think your handwriting might be terrible like mine and you don't want me to see it, then you can do it that way. Or if one person is better at bookkeeping, so if you're afraid you're going to lose it, for example, you can have, do it that way. So I'll leave it up to you, whichever way that you want to do it. But all right, so the second problem says, okay, so we have an object of length L, cross-sectional area A, and a mass of M floats upright in a liquid of density rho. Okay. So here, first thing it wants to do is say, okay, so the object is simply floating. So we want to determine the height, which is underneath of the fluid. Then we're going to apply a force F downward to push that thing down so that it changes to a new height, which is then H plus X. And then finally, we want to relieve that force and then see what happens. Well, what's going to happen is, if you've ever been in a boat before, when you're standing in the boat gets pushed down, and then if you jump out of the boat ends up harmonically oscillating up and down. So what you're looking for then in part C is the period at which this object or the boat is going to harmonically oscillate. So let's take a look at our free body diagrams. Let's kind of see what's going on. So let's say here is my object. So this thing has a length of L. So L is across this axis, has a cross-sectional area of A, and this thing, say, initially is in the fluid. So it's at this height here. So this is the height h that we're looking for. So how much is it underneath of the fluid? And our fluid has a density of rho. And let's say this thing has a density of object. So afterward, we're then going to, oops, that's a horrible line. There we go, that's better. We're going to apply an extra force F downward. And then this is going to be at a new height of h prime, where h prime is equal to this h over here plus an extra distance of x. So x then is going to be, say, this extra distance here. Afterward, we're going to relieve F, which means we're going to take our hand away, and this thing is going to end up accelerating upward with an acceleration of A, so that this thing is going to harmonically oscillate up and down. So let's think about our free body diagram, right? So here, this thing has a weight to it, so it has an mg downward. So this is our free body diagram from him. And he is inside of a fluid, which means there's a buoyant force pushing upward, where this is then going to be our buoyant force F of B. Okay. F of B, remember, is equal to the density of the object times the volume of the fluid, which is being displaced. So that's the volume of the fluid, times then the acceleration due to gravity. Now here, the volume of the fluid is the volume of the fluid which is being displaced, which in this case is then going to be that cross-sectional area A, times then the height h, because this is the volume here which is being displaced. Right? This is my volume of my fluid. So this is my free body diagram for the first part. In the second part, it's basically the same way. I still have the buoyant force upward. We still have the gravitational force downward. But what's different now is we have this extra force F pushing downward. In part C, again, we have mg pushing downward, but that force is gone, so we still have what? The buoyant force pushing upward. So again, basically what it's trying to do is bring you through steps on how to figure out what is the period at which this thing is going to harmonically oscillate. So basically what will happen is that this thing is going to oscillate up and down with a period of t. So I'm kind of bringing you through the steps on how to figure out how fast this thing is actually oscillating. So what is the period at which this thing is oscillating? But this is all the information you need to know. So for part A, use that free body diagram. For part B, use that free body diagram. And then for part C, use that free body diagram. So in each cases, you're just going to use that the sum of the forces is equal to ma. Right? But for part A and B, it's a static situation, which means the acceleration is simply equal to 0. So it's sum of the forces must be equal to 0. Okay. It's okay?
Mm-hmm.
I'll be back to check on you. So, okay. Right. So, yeah. Give you about another 20 minutes or so to kind of get started on that one. Mm-hmm.
So we can get done with it.
How we doing, ladies?
We finished.
Good. Very good. So if you're done with that one, then let's start talking about the second one. So let me bring that one up. And then again, I'll kind of describe what's going on, and then I'll give you about another 20 minutes to kind of start working on that one. This one is a little more challenging, so we'll talk about it. So this one says is we have an object of length L and mass M and cross-sectional area A is floating in some fluid which has a density of rho. So in the first part, basically it's just floating on top of the fluid, and what you want to do then is determine how much of the object is underneath the level of the fluid. So by how much is it floating? The second part then says we're going to apply a force F downward onto it, and we want to figure out what is the new amount of the object which is floating under the fluid. So if you want to think about it, there's a boat sitting on the water. So initially there's an amount of the boat underneath of the water. Then you step into the boat, you apply an extra force downward so the boat goes down further into the water. Then the last part then says, let's suddenly take away that force. So for example, you jump out of the boat. Once you jump out of the boat, what happens then is the boat is going to accelerate upward, but it's not going to stop. It's going to carry up and then slam back down and then actually undergo harmonic oscillation. So your boat, when you jump out of it, ends up going under harmonic oscillation. And part C is trying to get you to determine what is that harmonic oscillation period. So what's the period of oscillation of this object once we take away that force F? So these are the free body diagrams that you're going to work with. So this is free body diagram from part A, for part B, and then for part C. So in part A, here's the length L, so that's the length of the object. On the top and the bottom, we have cross-sectional area A. This thing has a density of the object and a density of the fluid. So we're looking for this height H here, which is the amount that it is submerged in the water. So here, since it has a mass, it has a gravitational force pulling downward, has a buoyant force upward. The buoyant force is then the density of the object times the fluid, which is being displaced by the object, times the acceleration due to gravity. Here, the fluid which is being displaced by the object is this part in red, which is then the cross-sectional area times that height H, which is submerged under the fluid. Part B, it looks pretty similar, except now there's the extra force downward, which means it's going to be submerged by an amount of H prime instead of H, which is then H plus X. So again, we still have that same buoyant force upward, except now it's right here, so the volume of the fluid displaced here is now going to be the cross-sectional area A times that H prime instead, because now it is submerged further. And then C, we're taking away that force F. So what's going to happen now is it's going to accelerate upward with an acceleration of A. So let me draw this line a little bit bigger. So this is my acceleration A. And then this thing is going to harmonically oscillate with some period T. So what we're looking for in this case is the period T. So the way we're going to do this is the way we did the other ones in class. You're going to start off by saying, okay, the sum of the forces must be equal to the mass times the acceleration. And then for part A and part B, the acceleration is simply equal to 0 because it's a static situation. So from there, you're just going to use all the forces acting on this must be equal to 0 to find the height here, find X here. And then in the third part, using the sum of the forces equal to the mass times the acceleration, since the acceleration is non-zero. And then from there, you want to do what we did in class, which is to eventually get that A is proportional to then omega squared times X, okay? So this is what we want to get our acceleration to look like. Once we do that, whatever shows up in front of X is the angular frequency squared. So once you have the angular frequency, then you can say, well, the period then is 2 pi divided by that angular frequency. So that's ultimately what we're trying to do. Is okay?
Okay.
This one's a little challenging, but I'm sure you can handle it. We're good. Okay. So I'll be back to check on you. Like I said, I'll give you about another kind of 20 minutes to get started on it, and then we'll go from there. Okay.
8.28.
How we doing, ladies?
We're having a conflict on answers.
Okay. So what happened?
We're on the last part, so part
Okay.
C. And I think we all solved the y equation and got the same answer.
Okay, so what did everybody get for the time?
We all got 0.539.
539. For the time?
That's what we got.
Okay. So how did we do it? So what did you write down?
We had x equals x naught plus v naught times time.
We used y though.
Yeah.
For
So call it Y. That's fine.
Yeah. I meant though, gosh. So v naught times time plus 1/2 a t squared.
Okay. And what's your coordinate system in this case? So is your coordinate system pointing upward or downward?
Upward, or well, it's downward.
Okay, so you're starting off with a block at y is equal to 0. Good. Okay, so you have it at y is equal to 0, and then in that case, gravity would be positive. Good. So in this case, what would be your y naught?
We put 0.
0.
0. Good. And what's your initial velocity in the y direction?
8 is what we said.
9.8. Wait,
That's the acceleration, but the initial velocity is,
what did you ask? I'm sorry.
I asked for the initial velocity in the y.
0.
0. Good. So in this case, we have y then is equal to 1/2 gt squared. That's right. And then by the time it falls, how far does it fall in the y direction when it hits the ground?
4.9.
Good. So you have 4.9 is then equal to 1/2 times 9.8 times t squared. Right? But what's 1/2 of 9.8?
4.9.
4.9. So you have 4.9 is equal to 4.9 times t squared. So the 4.9's cancel. So you have t squared is equal to 1. So what's t?
1.
1. Good. So there's the source of part of our problem. So good. So now if we put that into the x direction, in the x direction we have, now it's just v naught times t, right? So v naught is 4, t is 1, so it has to travel, what's 4 times 1?
4.
4. Good. So it has to go 4 meters. That's right.
So is it x equals 12?
X equals 4. That's it.
I think I'm still confused.
Okay. So here, let me
So x naught is 4, correct?
correct.
Okay, and vi in the x direction is 8.
No. VI in the x direction after the collision is 4. So we don't care about what's happening before the collision, only
That's
what's
what-
after the collision.
Okay.
So were you adding the two velocities together? I think that's what it sounds like you were doing.
I think so.
Okay. Gotcha. Yeah, so the only velocity we care about for M1 is that after the collision, so that 4 meters per second.
Okay.
I'll be right back.
And
Yeah.
Hello.
Hello.
You asked for help?
Yeah, we all ended up in the same place basically, but it just happened to be not the same place that you ended up.
Okay, for which part? Part A?
A.
Okay, so let's talk about it. So let me share my screen again. So let's come up here. Let me add a new page. Okay, so good. So let's look at part A. So let's draw our Freebody diagram. So again, we have what? Mg downward. So this is Mg. And we have our buoyant force upward. So here's FB. So here we would then say what? The sum of our forces is equal to 0 because there is no acceleration, it's just static. So we get our buoyant force minus the weight is equal to 0. The buoyant force we know is then the density of the fluid times the volume, which is going to be the cross-sectional area times h times g, minus then the mass of the object, which we're going to write as the density of the object, times then the volume of the object, which is going to be the same cross-sectional area, but times the length of the object, because that's the entire volume, times g is equal to 0. So the g's are the same, we cancel those. The a's are the same, we can cancel those. So we get rho times h minus rho 0 times l, well, that's horrible writing, is equal to 0. After I learned how to write.
I'm lost.
So rho 0.
I got lost. I'm lost at the step where you converted the volume of the object to A and L.
Oh, okay. So my object, remember, is this thing. So here is my object. So we know is that this has a side length of L and a cross-sectional area of A.
Mm-hmm.
Right? So we can then say the volume of the object is then equal to the length times the width times the height, but the width times the height is just A. Less than just L times A. Okay. And then here, right, I'm using that the mass of the object is equal to the density of the object times the volume of the object.
Okay.
So that's then going to be the density times L times A. Is everyone okay?
I had done it where I'm with you. I had gotten it to M equals length times width times height times density. I crossed the G's out.
Right.
And then mass equals area times height times density. So I didn't take.
Right, so you went to rho times A times H minus M is equal to 0.
Yes.
Yes, good. That's right. So here, then you would say H then is equal to what? M divided by rho A, right?
Right.
Good. So the only thing I'm doing now is I'm using this extra step that the mass is actually this, and now I'm substituting it in here.
Do you have to?
Well, I mean, not necessarily. So if I only gave you the mass of the object, then no, you would not have to do that. So in this case, you would have to know the density of the object.
Okay.
Yeah. So you're just leaving it here, which is absolutely okay. I'm just taking it one step farther and saying, I know the density of the object. So then I'm just going one further step. So that this is going to be rho 0 over rho all times L. So that's the only difference.
Okay.
Yeah. But yeah, Adrian, you're basically the same part that I am. Yeah.
Okay.
Yeah. Was okay?
Yeah, that's, I think, what we had all done. And then we were like checking our answer on the PowerPoint and we're like, how are there 2 densities in here?
Yeah, so I'm just assuming that we know the density of the object. That's
okay.
So, yeah. You okay, Callie? You look a little... No, where did we lose you?
I'll just stare at it more. Maybe it'll happen, but.
There you go. Is okay? Kids are awake. Okay.
All good.
Okay.
Oh man.
All right. I'm gonna check on the other groups. I'll be right back. Okay. How do we do, ladies?
I think we figured out the first one.
Good. Good. All right. So if we're all okay on the first one, let me bring up the second one and let's talk about the second one. I'll get you at least started on that one. So where are we? Here's the second one. So the second one's actually, it's kind of challenging, but I like it because it actually shows we can do interesting things with the limited amount of physics that we actually know, but let's talk about it. So this one says that we have a, say, rectangular shaped object, right? So a 3-dimensional object, which has a length of L, a mass of M, and a cross-sectional area of A, and it floats in a liquid with a density of rho. So in the first part, it wants us to say, okay, so the object is just sitting in the fluid. Part of it is going to be underneath the fluid. Let's call that amount H, and we just want to know how much is that amount H. So how much of it is floating under the fluid. In the second part, now we're going to say, okay, let's push down with it with amount of force. So if you want to think about this as a boat. So initially, the boat is sitting in the water, and then you get into the boat, right? What happens to the boat? Well, the boat sinks down further into the water. Right? So now what you're looking for in this part is how much further did the boat sink into the water? So now the last part, part C, is saying, okay, let's suddenly take away that force F. So if you want to think about it, you're standing in the boat, you jump out of the boat. What happens to the boat? Well, the boat now is going to accelerate upward, but it has too much momentum. It's going to pass the equilibrium position, and then it's going to come back down due to gravity, and it's actually going to harmonically oscillate. So what you want to know then is, what is the oscillation period of the boat? Best way I can kind of describe it. So let's look at the free body diagrams for each part. So in the first part, for part A, here's our free body diagram. So we have, here's our object, cross-sectional area of A, length of L. This is floating in the water. It's submerged by a height of H, which is this amount. And then it has a volume which is being submerged under the fluid. So our free body diagram says we have weight pulling down, mg. We have a buoyant force pushing upward. Remember, buoyant force is the density of the object times the volume, or sorry, the density of the, density of the fluid times the volume of the fluid times then the acceleration due to gravity. So in this case, the volume of the fluid, let's bring that back. The volume of the fluid is just the amount of volume which is actually submerged under the water. Okay, so this is the volume of the fluid. There we go. So in this case, since H of it is submerged under the fluid, then it has cross-sectional area A times H, so the volume of the fluid is A times H. In the second part, we still have the buoyant force pushing upward. We still have mg downward, but since we're pushing it down, we have this extra F downward. But since more of it is submerged under the fluid, call that H prime, then the volume of the fluid which is being displaced is greater, which means the buoyant force is also greater. Part C, we're going to take away F, and now it's going to accelerate upward so that this thing harmonically oscillates with a period of t. So the way that we're going to do this is by looking at the sum of the forces. So we know the sum of the forces is equal to the mass times the acceleration. For part A and B, the acceleration is simply 0 because it's just floating, it's just sitting there. So what we want to do in part C then is use the information from A and B to then use the sum of the forces equal to ma, isolate A, and get that thing proportional to the angular frequency squared times x. So again, whatever shows up in front of x is the angular frequency squared by definition. So you're just going to read it right off of what you write. Then we know the period is going to be 2 pi divided by that angular frequency. So again, the point here is to use part C here to write the sum of the forces is equal to ma, isolate A using the information that we know from A and B to then rewrite the acceleration as omega squared times x. Whatever shows up in front of x is omega squared, read that off, and then use that into the expression for the period. So again, ultimately, I'm taking you through the steps. So the point of this problem is to go through the steps to determine exactly what is this period. So that's what we're ultimately trying to do. But I'm doing it piecewise. So we're going to do it a few steps at a time. Okay. Everyone okay? Don't be too scared.
No.
It looks bad initially, but it's not too bad. Okay. You don't look like you trust me, Miranda.
I'm very confused.
Okay, so just start off with A. We'll go that way. So basically from A, all you're going to do is look at the sum of the forces and say the sum of the forces, so you have the buoyant force minus the weight is equal to 0. Use the definition of the buoyant force and then just solve for that height of H. So that's it. So let's just concentrate on that part for now. And then we'll go back to the other parts. Okay.
Okay.
Sounds good. Oh, did I take it away too soon, Miranda?
I took a picture. You're good.
Okay, good.
Or like where I am now, I guess I'm probably not done, but I have M plus F over.
Hi, ladies. Sorry it's been a little while, but how are we doing so far?
Not
We're
well.
stuck with the
We're
first
stuck.
one.
We're
Okay.
very confused.
Okay, how far did we make it so far?
First question.
Yeah, first.
Part A? Okay, so let's talk about it. So let me share my screen here, and then let's talk about it. So, good. So basically, all we need to do is, again, let's first start off by drawing our free body diagram. So here is my object. This thing is, say, floating, so that this is H And then down in this direction is mg. Up here is the buoyant force, right? So good. So now what we're going to say is that the sum of the forces acting on this thing is equal to 0 since it is static. Okay, so let's say this is my y direction. So the sum of the forces in the y are equal to 0. So it's going to give me my buoyant force minus my weight is equal to 0. Okay? Buoyant force we know is equal to the density of the fluid times the volume of the fluid which is being submerged, which is this amount. So it's going to be equal to the cross-sectional area A times the height times G minus then mg is equal to 0. Okay? Now this G is the same as that G, so we can cancel those out. So what this says then is that what? Rho times A times H is equal to M, right? So the density of the fluid times the cross-sectional area times the height is equal to the mass of the object. Solve that for H. H then is going to be equal to M divided by rho times A. Now, if you want, which is what I did in the problem, I said, well, the mass of the object is the same thing as the density of the object times the volume of the object, which is the same thing as the density of the object times the cross-sectional area times the actual length of the object. And then plugging that in here, that gives me the density of the object divided by the density of the fluid, all times the length. That's where this comes from. Everyone okay?
Okay.
Okay. So now for part B, so let me open up a new page. So part B is almost the same. So now we're going to have, here's my object again. But now we have an extra force F downward. So this thing is now going to be submerged further, right? Where this is now going to be submerged by an amount of the original height H plus some extra amount of X. Okay. But we still have the buoyant force pushing upward. We still have the gravitational force downward. We still have a static situation. So again, we still know the sum of the forces in the y direction are equal to 0. Again, let's take that this is the y direction. So now we have the buoyant force minus the weight minus the force F is all equal to 0. Everyone okay?
Mm-hmm.
Now here we just want to solve for what is this F. So we're just going to add F to both sides. So F then is going to be the buoyant force minus the weight. Now the buoyant force is basically the same, except now it's the density times the volume again, but the volume of the fluid has increased because now it's at an amount of rho times A times H plus X, because now this is increased by that amount, times G minus mg is all equal to F. Okay. That was okay? So at this stage, now all you have to do is use this H that you just solved for here. So either use it in this form or this form, whichever one you want to use is fine. It just depends on how you write M on the next page. Substitute that in here for this H, and then solve for F. So you're about 90% of the way there. So now just replace this H with previous H. And then simplify. Is okay? You don't look very convinced, Emma. You doing okay?
Yes.
Okay. Molly, Jolie, you doing okay?
Yeah, so we solve for F?
Solve for F, that's right. So you're just looking at what is the force that you're applying to push it down. Or sorry, no, you're not solving for F. Sorry, you're solving for X. Sorry about that. I misremembered. No, you're solving for X. Sorry. Sorry. Yeah. So simplify for the children are awake. Okay, for X. There we go. My 2-year-old daughter is the loudest person I've ever heard in my life, so it's fine. Everyone's okay? So far, so good? Okay. I'll be back.
I don't think you could subtract the G because it's like attached.
I meant divide. Sorry if I said subtract.
How we doing, ladies?
Not well.
Not well.
A little rough.
At least we're honest, so that's good. So where are we? We're on part B?
Yeah.
Yeah.
Okay. So how far did we make it so far?
Well, we thought we made it all the way.
And
But
then we checked.
I don't think we did.
Okay. Well, let me share my screen. So I was already working on this with somebody else. So basically, for part B, so again, here's our free body diagram. So we have FB upward, we have MG downward, but we have this extra F downward. So now it's being submerged by an amount of H plus X, right? So now we're going to do the same thing. We're going to write that the sum of the forces in the y direction is equal to 0. So we have the buoyant force minus the weight minus F is equal to 0. So here the buoyant force is now going to become the density of the fluid times cross-sectional area, but now it's submerged by an extra amount of X. So now it's going to be H plus X times G minus mg is equal to F. I just brought F to the other side. So at this stage, all you want to do now is use that H that you saw for in the previous case, substitute that in here for this H, cross things out, and now solve for X. That's all we're doing.
I think the crossing.
You're
Where we're-
substituting the last one.
So I think we decided to substitute too late.
Oh, you tried to manipulate some things and then substitute?
Yeah, we tried to like completely solve for X, then plug the H in.
Gotcha. Now, it's easier in this case to plug the H in first, because basically what you're going to see is this H term with the rho and the A is going to basically turn into an mg term. So this first term is going to be mg, which is going to cancel with this mg, and then you're just left with this extra term. So if you do it earlier, you'll kind of see that first. So.
Okay.
You guys doing okay?
Yeah.
Sorry, you can hear my daughter in the background. So. She's only 2, but she's probably the loudest person I've ever heard in my life. So it's fine. Okay.
Professor Pollock's kids used to like run across the screen and his cat would walk across the desk.
Yeah.
I think I'm.
All right. How are we doing, ladies?
No.
Gotcha. How far did we make it so far? Did we get part A?
We're working on it.
Working on it still? Okay. It's hard to do it with a dog in your face too, but it's fine.
Yeah, he's the worst.
Gotcha. Okay, so let's talk about part A.
Well,
So that
can
means-
I tell you what we got for part A? Can you say if it's okay
Sure.
or in the right direction?
No
Well,
problem.
We kind of got this. Well, we got H equals like the mass over A.
Yeah, that's it. So H is equal to M over rho A. The only thing I did separately, which is if you're comparing to my answer, is I wrote the mass was equal to the density of the object times the volume of the object. So that's what I did here. And then the volume of the object is simply A times L. So yeah, so plugging that in, that's what gave me the rho 0 over rho times L. But yeah, no, you're absolutely right.
Oh, goody. We got it right.
Well, right. I'm proud of it.
No, that's absolutely right. Good job. So good. So for part B then, let's switch over to part B. So here, the only thing that's going to be different now is you have this extra F downward. So, but that extra F downward causes the object to submerge more, which means that instead of having H submerged, now it's going to be H plus X submerged. So if we do the same thing as before, so we do the sum of the forces in the y direction, we get buoyant force minus the weight minus F is equal to 0. But now the difference is that the buoyant force is now going to be rho times A plus, or H plus X instead of just H. So once you get it into this form here, what you want to do is use that H that you just solved for, plug that in here for this H, and then simplify and solve for X. Okay. So at this stage, you're about 90% of the way there. So all you want to do is now take the previous H here, substitute it in for this H. What you'll notice is that this first term is actually the same as this term, so those two things are going to cancel, and then you're left with this is equal to F. And now just solve for X.
So the F is the buoyant force or the push force?
The F is the push force. Yeah,
Okay.
that's right. Yeah, all of this term here is the buoyant force. So we've already used that part. Yeah.
Okay, that makes sense.
Okay. So yeah.
So we just solve for X, and then do we plug that into A equals the W to the second X?
That'll be in part C. So
Part C.
that'll be part C. So no, so for now we're just solving for what X is. So that's fine. So what you're gonna do in part C then is you're gonna actually start off with this expression that I've highlighted, but you're gonna say F is now equal to MA. That's the only thing that you're gonna do. So basically for part C, you're still gonna start off with rho times A times H plus X times G minus mg is now equal to ma. So that's going to be the only difference. Okay. You're still going to use that previous h from before, but you're not going to do anything with x. X is still going to be a random variable. So you're not going to use what you did in part B for x. And then what you want to do from here is eventually just solve this for a. Okay.
Okay, when we solve it for A, do we still do the one that I just said?
Which one did you say? Sorry.
The A equals the W squared X?
Correct. Yeah. So eventually what you're going to get is you're going to get something for A, and you're going to say A then is going to be X times something. This something here is going to be omega squared. That's right.
Omega.
Exactly. That's right, Mallory. Okay.
Cool.
Good. Everybody's okay? So once you get it into that form, you just read off what omega squared is. That's it. So whatever is in front of that x or next to that x is omega squared.
Okay.
Okay. Good. Good.
Numbers, then we'd be able to plug it all in, and like
And
we
then
would
like,
if we have to solve for
the
x
math,
to
it would
start.
still be right. Yeah.
All right. How are we doing, ladies?
We're still stuck.
Well, I think we have all the parts right.
Okay.
Like when I look at my paper, I have all the components in the right in the equation correctly. Then to derive it to where it's x equals is not.
Okay.
It's a no-go for
So let's take a look. So let's see where we're going wrong. Okay, so again, we have rho times A times H plus X times G minus mg is equal to F, right? And we also know that H is equal to M over rho A, right? So we all agree on these things.
Yes.
Good. So let me start off here, and I'm going to expand this part first. So it's going to be rho times A times H times G plus rho times A times X times G minus mg is equal to F. Everybody's okay?
Okay.
So I'm just expanding this first term, right?
Yeah,
Everybody's okay?
I was plugging H in. Yeah, I was plugging H in before expanding.
Okay, we're gonna do that now. So we could have done it before, but we're gonna do it now. So now I'm gonna take this and plug it in here. So this is gonna become rho times A times M over rho A times G plus rho A x G minus mg is equal to F, right?
Okay.
Now what happens to this rho A here?
Cancels.
They cancel. So this is rho A, rho A. So this is now mg plus rho A x G minus mg. So what happens to those two mg terms?
They cancel too.
Cancel, good. So this term cancels with this term. So now I'm left with rho A x G is equal to F. And now solve for x. So x then is equal to F over rho A G. It's okay?
That makes so much more sense.
It makes sense when you see it, but like I would not have, obviously I would not have started there because I didn't. Yeah.
So let's talk about C real quick. So for C, the only thing that's going to be different, I'm going to tell you a little trick about C, and I'll let you think about it. All we're going to do is we're going to let F go to MA. That's the only thing we're going to do.
Because I texted and said, can I call you back?
Right? Which basically means if we go back to what we had here, we then have rho times A times X times G is simply equal to MA. Now solve for A. So A then is going to be rho times A times G divided by M, all times X is equal to A. Is okay with us?
Yeah.
Does that say rho A x G?
Rho A G over M times X. Yeah. I'm just switching the order of X and G. That's it. Because I want to get X by itself. And the reason I want to do that is because remember that we wrote down that A is equal to omega squared times X. So basically, if I compare this guy to this guy, what that tells me then is that omega squared is then equal to rho AG over M. So my angular frequency squared is whatever shows up in front of that X, which is this term. So this is my angular frequency squared.
Why isn't the X over M?
Well, I'm multiplying, so it doesn't matter how the X shows up on there, right? Because the order of operations and the order of multiplication doesn't matter.
Okay, yeah.
Right, so all I'm doing is I'm just pulling out the X to the side, so that way you can see that this term here is the omega squared. So I'm just making it easier to identify.
Okay.
So that's the only thing I'm doing. But yeah, if I want to write this as X rho A G over M, all that's the same thing. So I'm just trying to get the X away to make it easier so I can identify. So, where was I? There we go. So I can identify that omega squared. That's the only reason why I'm doing it. So just to make it easier to identify.
Okay.
From here, you use your like T equals 2 pi over W. And
correct. So now that I have omega, so now you're just going to say that T then is going to be T 2 pi over omega. Exactly. So once I now identified what omega is, I can now just use that into here. Exactly. That's right. And now you guys have everything. And that's it.
For some reason though, how does it go from A times rho times G over M to M over rho times?
Oh, because the omega here is on the bottom, right? So here, this is omega, so this means that omega is equal to the square root of rho A G over M. But now when I bring it over here, I have to invert that. So for example, if I had A over B was equal to Y, then 1 over Y is equal to 1 over A over B, which is the same thing as B over A. So when I invert it, I just put the denominator on top. Is that okay? Good. Okay. Well, good job, ladies. Looks like we're out of time for today. So if you're okay with all this, then you're free to go, and I'll see whoever shows up for the lab portion. Okay.
All right.
All right. So I'll see everybody tomorrow or later.
Bye.
Yeah.
Bye.
There he is.
I'm coming. Sorry. What's going on?
I didn't know if we needed to say if you were coming back or not.
Oh, I'm working on it. Yeah. So how we doing, ladies?
I think we feel good on the t equals 2 pi times the square root of m, but I was confused on how you got instead of k.
Instead of what?
It'd be times the square root of m over k.
Oh, I see. So that comes in part C. So remember, in part C, what we're doing is now you're replacing F with MA. Once you do that, you have to isolate A, and then once you have A isolated, all you're going to do is get A is equal to something times X. Whatever shows up in front of that X is the angular frequency squared by definition. Okay. So the K only shows up in your other one because it had a spring constant. Remember, we got it by saying that K times X was equal to MA, so we divided both sides by M, so we got K over M times X was equal to A, so that meant that the angular frequency was the square root of K over M.
So you're telling me whatever was in front of the X is what goes, it'd be M over what was in front of the X.
Correct. So as long as you have, that's right, something times X is equal to A, then whatever's in front of that X is omega squared.
What goes, okay.
That's right.
Now I got you.
Good. Good. So if I share my screen quickly with you. So basically, if you go back to what you had here for your X is equal to F over rho AG, all you're going to do is let F go to MA, rearrange that, and then you should get that rho times A times G over M times X is equal to A. So whatever shows up in front of that X is the angular frequency squared. So if I identify this, then I can say that omega squared is rho AG over M, which means rho then is the square root of all that stuff. Okay. Now that I know that's omega, I'm just going to plug that in for the period over here and then be done with it. Okay, Mallory?
Yeah.
Good. Right. So, sounds like you guys are on a good track. So we're officially out of time. So if you guys are okay, then you can take a break before the lab starts if you come to the lab. Otherwise, I will see you tomorrow then, if I don't see you for the lab portion. Okay. Everybody's okay? Smiling faces, good. Okay. So we're doing good. All right. So I'll either see you in a little bit or tomorrow. Bye.
Points. Like we ended the class. He had 2,000 points in his class. Like everything was worth like 100 points. Doesn't matter what it was. So
We're waiting on him. Are we supposed to leave? Can we leave yet? We've been done.
I'm here.
Oh, he's back now.
All right, I was talking to another group. If you're done, yeah, we're officially out of time. So yeah, you can take a break before the lab starts. If you come to the lab, then I'll see you then. Otherwise, I'll see you tomorrow if you don't have any questions. So you guys doing okay? You have any questions before you take it?
How do we, so, sorry, Emma.
sorry, that was the same question. Like, what are we supposed to do with this? Do we submit it?
Well, you won't submit it until the day of the exam. So basically what will happen is, so on the day of the exam, you're going to go onto Blackboard. There'll be a link that says, you know, exam 1. And then under there, there'll be a bunch of different links for submissions. One of the submissions will be for the group assignments. So in that case, you can either all submit your own version, or one of you can write down everybody's name that was part of the group, and then go ahead and submit one on behalf of everybody else. And then I'll give everybody a point for those. So each one of these that you complete, so as of today, you now have 2 points of extra credit for the exam. As long as you submit, you know, at least that one version. So whichever one is easiest. So if somebody is a good bookkeeper and you're not going to lose it, make sure write everybody's name. So if you're afraid you're going to lose your own copy, then just have one person write everybody's name. Or, you know, you can submit your own. It's completely up to you. But at this stage, you basically just want to hang on to it and then take a picture of it or scan it, so that way you can submit it for those extra credit points for the exam.
Okay.
Okay. So yeah. So for now, just kind of hang on to them and then submit them later. That's okay. So any questions on anything? That was the only question. Everybody's doing okay? All right. All right. So either I'll see you a little bit for the lab, or I will see you tomorrow.